All right, welcome back. So if you are skipping right past the previous video to this one and want to know what did you skip, what you skipped was a partial proof that the derivative of the sine of theta is equal to the cosine of theta. A similar mechanism can be used to prove that the derivative of cosine of theta is equal to negative sine of theta. So you don't need to know those proofs, but you do need to know the results. You need to know these formulas. What this gives us is it gives us an addition to our existing formulas for derivatives. We have derivatives of constants being 0, derivatives of power functions following the power rule, derivatives of exponential functions following the exponential derivative rule, and derivatives of log functions following that log derivative rule. We combine these with product, quotient, and chain rules, as well as the rules that we tend to use but not think about. The derivative of a sum is equal to the sum of the derivatives. The derivative of a constant times a function is the constant times the derivative of the function. So we add these two new trig derivatives to our big list of rules and shortcuts, and not worry about the definition of the derivative and try to do everything from first principles, because it's kind of slow to do it that way. Now, recall that we have a bunch of other trig functions. We have the two that were just mentioned, sine and cosine, but we also have tan, cosecant, secant, and cotan. And their derivative formulas are quoted here. A little note about the notation. This notation, secant squared of x, isn't a very nice notation. I don't like it. Wish it didn't exist, but it does. What it means is it means secant of x all squared. Likewise, if you see sine of x, sine 2x, sine power 2x like this, this is a shorthand to save you on writing brackets of sine of x all squared. That's what that notation means. These are hard to memorize. They're not very friendly, in particular the cosecant and the secant ones. They get mixed up all the time. One thing that helps you remember these, there's no cosmic reason for this. Like, there's no special feature about the letters of the human alphabets, especially not the English alphabet. There's nothing special about that in relation to mathematics. However, if you look long enough, you'll find a pattern in anything, including in this. The pattern is a non-cosmic justice pattern. It has nothing to do with mathematics, just a fluke. Is that the derivative of a trig function that starts with the letter C is negative of something else, the negative of a different trig function. So the derivative of cosine is negative sine of x. The derivative of cosecant is negative cosecant of x times cotan. The derivative of cotan is negative cosecant squared of x. Again, it's just a fluke. There's no universal truth that is uncovered with this fact. This is just a memorization trick. Like SOHCAHTOA is a memorization trick. It's the same type of thing. But all these formulas here in blue, where do they come from? So if you want to know where the green ones come from, look at the previous video, and that will show you the reasoning of it. But the blue ones, they don't come from that. At least not as easily. You can use geometry to prove them, but I don't recommend it. What I recommend instead is using the green ones as building blocks, saying, all right, so if we accept these are true, or you look back at the previous video and you follow through the geometry, and then you don't have to believe anything, you just know it's true, then you can use those as building blocks to define the derivatives of the other trig functions. I'll show you how it works for the tan function. Y is the derivative of tan of x secant squared. So it starts by saying that we're going to take the derivative d by dx of an equivalent expression to tan of x, which is sine of x, over cosine of x. Now, how do we take the derivative of such a function? We have to use a quotient rule. This is a t over a b. So we're going to have bt prime minus tb prime all over b squared. Our top function is sine of x. T prime is cosine of x. Our bottom function is cosine of x. When we have to use our green formulas from the previous slide, the derivative of cosine of x is negative sine of x. So I'm going to plug those into this formula. We we have the bottom function, cosine of x, times the derivative of the top. So we got cosine of x, minus the top function, sine of x, times the derivative of the bottom, which is negative sine of x, divided by the bottom squared, which is cosine of x all squared. And then we can simplify. Cos times cos, I'm going to convert to evil notation, cos squared of x. Negative sine times negative sine is positive sine squared of x, again in evil notation. And the bottom, we have cos squared of x. And there's a few ways we can proceed from here. We can either split this up into two fractions, cos squared over cos squared plus sine squared over cos squared, which is 1 plus tan squared, and then use a trig identity. For what is 1 plus tan squared, it's secant squared. Or use a different trig identity. This trig identity, cos squared x plus sine squared x is equal to 1, is actually just Pythagorean theorem in stealth mode. If you take SOHCAHTOA, so op, add, pipe, and you rewrite sine, opposite over hypotenuse, rewrite cos, adjacent over hypotenuse. Then sine squared is opposite squared over hypotenuse squared. Cos squared is adjacent squared over hypotenuse squared. Hypotenuse or opposite squared plus adjacent squared is equal to hypotenuse squared. You can rearrange the sum of those formulas, cancel out the hypotenuse squared, and you get that sine squared plus cos squared is equal to 1. So it's not something new, it's something you can derive if you wanted, or you can just take it as fact. So you get 1 over cos squared x, which is secant squared x, as needed. I don't recommend doing that. I recommend memorizing it, or making a giant list of formulas on paper. So have these listed with your, make a giant list of derivative rules, tack on the other functions down here, the other 4 derivative rules, have your full set, have them all in one spot. Cosecant, very quickly, this is the derivative of, what is the definition of cosecant? 1 over sine of x. You can use a quotient rule if you want, or you can use the chain rule. I'll use a quotient rule. So bt prime minus tb prime all over b squared. So the bottom function, sine of x, multiplied by the derivative of the top, which is 0, minus the top, which is 1, times the derivative of sine of x, which is cosine of x, divided by sine squared x. We end up with negative cos of x over sine of x times sine of x. Gotta use a little trick here. This is negative cos of x over sine of x multiplied by 1 over sine of x. Just splitting up the fraction that way. Cos over sine is cotan. 1 over sine is cosecant. And it's usually written as negative cosecant of x times the cotan of x, just changing the order of multiplication of those terms. It doesn't matter what order you multiply two scalar quantities in. So that one we didn't need a special trig identity, sine squared plus cos squared is equal to 1. We just needed what the special trig functions are in terms of non-special trig functions. Convert everything to sine and cos, work with the sine and cos derivative formulas, and then go backwards. Go back to the the unfriendly trig functions. All right, let's do some more complicated examples using our derivative formulas for the trig functions. So we're just going to take those as kind of definitions now. We're going to take them as a given that the derivative of sine is cosine, the derivative of secant is sec x tan x, and all the other ones. All right, so the first example here, we have the derivative of x cubed multiplied by sine of x. We need to use a product rule. I'm going to call this an a times a b. F prime of x is then ab prime plus ba prime. So x cubed times the derivative of sine of x, which is cosine of x, plus 3x squared b prime, or a prime, times sine of x. And that's it. Don't do anything fancy. Don't do any weird factoring. Don't use any trig identities. Do not factor. Do not use trig identities. Do not do heroic simplification. Please do not do any of those things inside this course. You may need to do those things in other calculus courses, Calculus 1000 if you take that, but please don't do that here. Okay, next one. We're going to take this derivative using a quotient rule. This is a top function over bottom function. So f prime of x is the bottom function times the derivative of the top minus the top function times the derivative of the bottom divided by the bottom squared. So the bottom function is x. Now t prime, we go flip back to your formula sheet. What's the derivative of tan? Secant squared. Eventually you'll memorize it. We'll do these enough. T, tan of x, times b prime, the derivative of 1 times x is 1, divided by x squared, and that's it. That's all we have to do. Maybe I'll just get rid of the multiplication by 1. So that's a non-heroic simplification. And I don't even want to know what simplifications could be done for this. Like you can take a cosine and put it in the bottom. I don't know why you do that, but you could. And then you could write it as x sec x minus sine of x over x squared cos x. Why would people do such things? I don't know, but if you've ever looked at the back of a math textbook, some people seem to enjoy doing that. Don't know why. All right, another example. And this highlights the importance of understanding the notation, understanding the evil shorthand. What is dy by dx, which means derivative, if y is equal to sine 3x. So you have to know what that means. What does sine 3x mean? This means sine of x all raised to the power of 3. Now this is a w to the power of 3. So we're going to use that old-timey, old-fashioned chain rule, despite having these newfangled functions. So for a function raised to the power of 3, the derivative is going to be 3 comes down, that function raised to the power of 2 multiplied by w prime. So let's plug in what we have. We have 3 times sine of x all squared multiplied by the derivative of sine of x, which is cosine of x. And then here's a non-heroic simplification. We'll do the evil thing. We'll convert this into sine squared x. And I'll get rid of the extraneous brackets. We don't need those brackets. And that's the most simplification that you would want to do. Who knows what other horrible things can be done? Sine of x times cos of x. There's an identity for that. Please don't use it. Here's another example. This time our trig functions have been plugged into a log function. when we take the derivative, we treat this as a ln of w. So as much as possible, we want to make this look like our old derivative rules and recycle our methods from before. The derivative of ln of w is w prime over w. It's nice to write that, right? No subscript x, no subscript y, at least for a moment. The reprieve is brief. All right, and we'll down the bottom we have tan of x plus sine of x. Now we have to take the derivative of that stuff. W is tan of x plus sine of x. W prime, derivative of tan is secant squared, referring to our list. Derivative of sine is cosine. That's what we'll put on top. Secant squared x plus cos of x. And that's it. Don't do anything else. Don't do anything heroic. Don't spend 1 minute on the question and then 10 minutes simplifying it. Leave it alone. Okay, another example. What do we do here? So reading the question and figuring out what is the format of it. What is the format of the derivative rule that we need? The big picture derivative rule that's hiding if you're not paying attention, not looking for it, is the product rule. It's an a times a b. So a is tan of x. In our product rule, we're going to have an a prime, so we're going to have to find the derivative of a, derivative of tan of x. We just used it, it's secant squared. B is e to the power of secant of x. Now how do we take that derivative? Make it look the way that allows us to use our old formulas. This is e to the power of function. We'll just call that function w. How do we take the derivative of e to the w? It's e to the w multiplied by w prime. So e to the secant of x multiplied by the derivative of the secant of x. Refer back to your formula sheet. Derivative of secant of x is secant of x times the tan of x. Okay, so we'll put all that together. F prime of x is ab prime plus ba prime. So a is tan of x. B prime is that big mess that we just created. E to the secant of x times sec x plus tan x. Or times tan x, what am I doing? Sec x multiplied by tan x. Plus b times a prime. E to the power of secant of x for b. And then our a prime is secant squared of x. And that's it. Don't do anything else. Don't do factoring. Weird factoring stuff. Weird textbook stuff. If this was a test question, the answer would look like that, except it'd all be one line. It's in 2 lines because I just can't fit it in. It's too long. All right, next. So we have the cosine of something. Cosine of some function with some function plugged into it. Let's make this look simpler. I'm about to introduce a new type of chain rule. The derivative, d by dx, of the sine of w is the cosine of w multiplied by w prime. D by dx of the cosine of w is equal to the negative sine of w times w prime. This looks a lot like the chain rule that we had before. D by dx of, let's say, e to the w is e to the w times w prime. We're just taking our derivative rules that have x in them. If it's a w instead of an x, we just have a w prime multiplied at the end. That's the only difference. And it's just the chain rule. So I'm going to use that. I'm going to take this expression, this cos of 3x squared, and we're just going to call what's inside there w. Y prime is then going to be negative sine of w multiplied by w prime. So negative sine of 3x squared multiplied by 6x. The traditional way that this would be written would to bring the 6x in front of the sine function. And the reason that actually has a good reason. That makes it so that you're not going to accidentally later on think that the 6x is inside the sine. It's multiplied by the sine function. It's not being plugged into the sine function. Only 3x squared is being plugged into the sine function. So that was some light simplifying for a good reason, just for clarity later on. When you flip back to and look at it, it's clearer that the 6x is being multiplied and not being plugged in. Right, and then there's another one. This time, not a polynomial is being plugged into the cosine function, but ln is being plugged in. But we're going to start the exact same way as the previous one. I'm going to rewrite this as the cosine of w. And use the same derivative formula. Derivative of cosine of w is negative sine of w. Derivative of cosine of x is negative sine of x. But we have to multiply by a w prime. Where w is equal to ln of x. So w prime, the derivative of ln of x is 1 over x. So we have negative sine of ln of x multiplied by 1 over x, which we can simplify, clarify what's going on. It's negative sine of the ln of x all over x. That would be our simplified answer. Let's say multiplying something by a half is the same as dividing it by 2. Multiplying something by 1 over x is the same as dividing it by x. All right. Blast from the past, something you may have forgotten, or maybe you thought you could get away from having to know it. But here it is. What type of function is this? What type of derivative rule do we need to take the derivative of x squared plus 3 all raised to the power of the cosine of x? If you're not looking for it, you'll miss it. This is the worst type of derivative possible. The base contains x. The exponent contains x. Despite not having any log functions, this is a logarithmic differentiation question. So here's how you go about doing it. Recall what we do whenever we're faced with a log differentiation question. What we do is we start by taking the ln of both sides. So the ln of the left side, the ln of f of x, is equal to the ln of the right side, the ln of x squared plus 3 to the power of the cosine of x. Now you use a log property. We're going to use log of m to the n is n times the log of m. So I bring the cosine down in front. If you look back at the notes, we're following the same example. Doesn't matter that we have trig functions now. It makes no difference. We'll do the same thing. Math is nice like that. Now we're ready for a derivative. We have all the rules that we need. Got to keep in mind that we have a product rule now. We have an a times a b. So we're going to do a d by dx of both sides. So the derivative of the left-hand side, the derivative of ln of w is w prime over w. The derivative of ln of f is f prime over f. And we have ab prime plus ba prime. So f prime over f is equal to a cosine of x times the derivative of the ln of x squared plus 3. That's a w prime over w. So 2x over x squared plus 3 plus b times a prime, the ln of x squared plus 3 multiplied by the derivative of the cosine of x, which is negative sine of x. Next, we'll cross multiply both sides by f of x to isolate for f prime. So we have f of x multiplied by all that stuff. I'm going to simplify lightly. I'm going to bring the cos with the 2x. So 2x times the cos of x over x squared plus 3. I move the negative sine x in front of the log function just so we don't get tempted to put the sine into the log function as part of the argument of it. It's not, it's multiplied by it. And then we really only have one step left. That's to replace f of x by the function. So x squared plus 3 to the power of cosine of x multiplied by everything that's there. 2x cos of x over x squared plus 3 minus sine of x times the ln of x squared plus 3. These are never very friendly. Every time you see a setup for log differentiation, it's always ugly. It's always the original function multiplied by two pieces that are added together or subtracted from each other, depending on whether a negative sign comes out or not. And there's other types of derivatives. I won't go through them, each one. You can try them out on your own. How do you take the derivative of each of these? So how do you take the derivative of the cos of 2 to the power of x? The square root of the cosine of x, the ln of the cos of x. So all these just are examples involving the cosine function. You could substitute a different trig function for each of these, and that's another question. The way to do each is described as follows. They're all chain rules of different types. We let w equal something, make the function look simple. So instead of ln of cos, it's ln of w. Instead of cos of 2x, it's cos of w. Instead of cos of x squared, it's cos of w. Cos squared of x is w squared. Remember, cos squared, like sine squared, means that thing all squared. It's a bad notation, but it's stuck. We're stuck with it. E to the cos of x is e to the w. Square root of cos of x is w to the power 1/2. Then use all the same derivative rules we would have used before, but with the new version of the chain rule that we have for trig functions. What I'll do in the next video is show you examples that don't fall into these templates, examples that are a little bit more challenging.